Semigroups and their representations, Lecture 2, Homomorphisms, Congruences and Quotients. Let us start with a discussion of the notion of a homomorphism of semigroups. Let S and T be two semigroups. Let us denote the semigroup operation on S by an asterisk and the semigroup operation on T by a star. Definition: a map phi from S to T is called a semigroup homomorphism, provided that, for all elements A and B in S, phi applied to A asterisk B is equal to phi of A star phi of B. Example 1. The identity map on the semigroup S is a homomorphism from S to itself. Such homomorphisms are usually called endomorphisms. Example 2. If S is a subsemigroup of T, then the natural embedding I from S to T is a homomorphism. Example 3. For any semigroup S, we have a homomorphism from S to the semigroup Ts of all transformations of S, which is defined as follows. Given an element A in S, we send A to the transformation lambda A, so that's a transformation of left multiplication with A. So this transformation is defined on an element B in S as follows. Lambda A applied to B is equal to A times B. So we multiply B with A on the left. So A is on the left of B. Example 4. For any semigroups S and T, and any idempotent E in T, we have a homomorphism from S to T which sends all elements of S to this idempotent E. Next, let us discuss the notion of a homomorphism of monoids. So let M and N be two monoids. We denote the monoid operation M by an asterisk and the identity of M by E. And we denote the monoid operation on N by a star and the identity on N by F. Definition: a semigroup homomorphism phi from M to N is called a monoid homomorphism, provided that it sends the identity of M to the identity of N. So phi of E should be equal to F. For example, the identity map on any monoid is a monoid homomorphism. Example 2. If M is a submonoid of N, then the natural embedding of M into N is a homomorphism. Example 3. For any monoid M, we have a homomorphism from M to the transformation monoid on M, which sends A to the transformation lambda A of left multiplication with A. That's exactly the same thing as for all semigroups. And the general remark about homomorphisms: as usual, a homomorphism is a map between two algebraic structures which intertwines the structure. So for semigroups, the only structure is the operation, so a homomorphism should send the operation on the first semigroup to the operation on the second semigroup. For monoids, we have the structure which consists of two parts, the operation and the identity. So a monoid homomorphism should send the operation to the operation and the identity to the identity. Now let's talk about congruences. Let S be a semigroup. Definition: an equivalence relation tilde on S is called a congruence, provided that it is stable under both left and right multiplication. That is, for all elements A, B and C in S, A tilde B implies both CA tilde CB and AC tilde BC. So if you have two congruent elements and we multiply with anything on the left, we get two congruent elements, and if we multiply with anything on the right, we get two congruent elements. Example 1. The equality relation on S is obviously a congruence, because there is nothing to check. Example 2, the full relation on S, so the equivalence relation which has only one equivalence class, which is S, so the whole relation consists of S times S. This is obviously a congruence. And example 3, Consider the additive semigroup of all positive integers with respect to addition. Define the relation tilde such that we have exactly two equivalence classes. A singleton class consisting of 1, and everything else joined in one equivalence class, 2, 3, 4, and so on. And it is easy to see that this tilde is a congruence. So if 2 is equivalent to 3 and we add any number, we get two elements from the same equivalence class. So this is a congruence. Next, let us talk about kernels of homomorphisms. Let phi be a semigroup homomorphism from a semigroup S to a semigroup T. Definition: the equivalence relation tilde sub phi on S, which is defined as follows. So A is tilde sub phi equivalent to B if and only if phi of A is equal to phi of B. So here A and B are elements in S. This is called the kernel of phi. Example: the equality relation is the kernel of any injective semigroup homomorphism. Example 2: if phi is a homomorphism from S to T, which sends all elements of S to some idempotent E in T, then the kernel of phi is the full relation S times S. So that's the equivalence relations with a unique equivalence class, the whole of S. And here is a proposition: the kernel of any semigroup homomorphism phi from S to T is a congruence on S. Proof: so two elements of S are tilde phi related if and only if phi of A is equal to phi of B. So A is tilde phi related to B if and only if phi of A is equal to phi of B. But phi of A equal phi of B implies that phi of CA, it is equal to phi of C times phi of A, because phi is a homomorphism. So phi of A is equal to phi of B. So phi of C times phi of A is equal to phi of C times phi of B. And again, since phi is a homomorphism, we can collect it into phi of CB. So A is tilde phi equivalent to B implies that CA is tilde phi equivalent to CB. And similarly for multiplication on the other side. So this is a proof of the fact that tilde phi is indeed a congruence on S. Let us describe all congruences on groups. Theorem: let tilde be a congruence on a group G. Claim: then there is a normal subgroup N of G such that the equivalence classes of tilde are exactly the cosets of G modulo this normal subgroup. Proof: we define our normal subgroup N as the equivalence class of tilde which contains the identity element E of our group G. To start with, let us show that N is a subgroup. Assume that we have two elements A and B in our class N. Then A is equivalent to E and B is equivalent to E. If we multiply the equivalence B equivalent to E with A on the left, we get AB is equivalent to A. But A is equivalent to E, this implies that AB is equivalent to E. And this means that N is stable under taking the product of elements. So this means that N is a submonoid of G. To prove that it's a subgroup, we also need to prove that it is stable under taking the inverse. So if A is equivalent to E, we can multiply this with A inverse on any side, and we get that E is equivalent to A inverse. So this implies that N is stable under taking inverses, so N is indeed a subgroup of G. Now let us prove that it is a normal subgroup. So if A is equivalent to E, then we take B in G and multiply with B on the left and B inverse on the right. We get that BA B inverse is equivalent to B times B inverse, which is E. So this means that BA times B inverse belongs to N, and so N is stable under conjugation with any element in G. So this means that we have already established that the equivalence class of the identity is a normal subgroup of G. Now assume that we have two elements A and B which are tilde equivalent. then we can multiply with B inverse on the right and get that AB inverse is still the equivalent to the identity. So this means that AB inverse belongs to n, but then it means that A belongs to n times B. So A is an element of the coset with respect to n generated by the element B. So two equivalent elements belong to the same coset. And we can reverse this argument. So if A belongs to NB, then AB inverse belongs to N, and so AB inverse is equivalent to E. Multiplying with B on the right, we get that A is equivalent to B. So two elements are equivalent if and only if they belong to the same coset. And this completes the proof of our theorem. Let us now dive deeper into the properties of congruences. So let tilde be a congruence on a semigroup S. Consider the set S modulo tilde of all equivalence classes with respect to this congruence. For an element A in S, we denote by A overlined the tilde equivalence class containing A. Proposition: for A and B in S, setting A overlined times B overlined is equal to AB overlined gives a well-defined binary operation on the set of all tilde equivalence classes. Proof. So what we really need to prove is that this formula gives a well-defined operation. It's a binary operation by definition, but the question is, why is it well-defined? Because we define an operation on sets by picking some representatives in these sets. So we need to prove that the outcome doesn't depend on the choice of representatives. So assume that A is tilde equivalent to C and B is tilde equivalent to D. Then, of course, AB is tilde equivalent to AD by multiplying B equivalent to D with A on the left. Also, we have that AD is tilde equivalent to CD by multiplying A is equivalent to C with D on the right. And now, by transitivity of equivalence relations, we get that AB is tilde equivalent to CD. So which means that the class of AB is equal to the class of CD. So if we change our representative from A to C and from B to D, the product doesn't change because we just get a different representative CD of the same equivalence class. And in this way, from this proposition, it follows that we have a binary operation on the set of equivalence classes, which is induced from the original binary operation on S. And of course, we get the corollary that the set of all equivalence classes with respect to this induced operation is a semigroup. And indeed, the associativity of the induced operation, it follows directly from the associativity of the original operation, as the induced operation is defined via the original operation. And the original operation is associative. So this semigroup S modulo the congruence tilde is called the quotient of S modulo the congruence tilde. And we also have the canonical projection, that's a homomorphism from S to S modulo tilde, which sends an element A in S to the tilde equivalence class of A, and this is an element of S modulo tilde. This is a surjective homomorphism from the semigroup S to the semigroup S modulo tilde, and it is called the canonical projection. Let us note that if M is a monoid with the identity element E, then for any congruence tilde on M, the quotient of M modulo this congruence tilde is a monoid, where the identity element is the class containing the identity element of M. And so for the monoids, we also have the canonical homomorphism, which is a homomorphism of monoids. Now we can talk about the image of a homomorphism. Let phi be a semigroup homomorphism from S to T. Definition: the subset of all elements of the form phi of A, where A is an element of S, that's a subset inside T, that's called the image of phi, and is denoted by im of phi. Proposition: the image of phi is a subsemigroup of T. Indeed, if we take two elements A and B in S, then phi of A times phi of B is equal to phi of A times B, because phi is a homomorphism, and of course phi of A times B by definition belongs to the image of phi. So the image of phi is closed under the operation. Example 1, the image of the identity homomorphism from S to S is the whole of the semigroup S. Example 2, the image of the canonical embedding of some subsemigroup S into some semigroup T is again this subsemigroup S. Now we can formulate and prove the so-called first isomorphism theorem. Let phi be a semigroup homomorphism from a semigroup S to a semigroup T. Then we have the following. First of all, the kernel of phi is a congruence on S. Then the image of phi is a subsemigroup of T. Moreover, the quotient of S modulo the kernel of phi is isomorphic to the image of phi. And this isomorphism is given by the following map. We take an element A in S, and we map the tilde phi equivalence class of A, and that's an element in S modulo tilde phi, to the element phi of A, and that's an element in the image of phi. Note that we have already established the first two claims. We know that kernels of homomorphisms are congruences, and images of homomorphisms are semigroups. And the map in the third claim is well defined and bijective. This follows directly from the definition of phi. So the class of A consists exactly of all elements which are mapped to the same element of T by phi. That's a definition of the kernel of phi. And this map is a semigroup homomorphism. We just checked it. It follows from the construction of this map. So this completes the proof of the first isomorphism theorem, and we can only note that this first isomorphism theorem works exactly in the same way for monoids. Now let's talk a little bit about ideals. Let S be a semigroup. Definition: a non-empty subset I of S is called an ideal, provided that for any element A in I and for any element B in S, both A times B and B times A belong to I. For example, the whole semigroup S is an ideal of S. Example 2, if our semigroup is a group, then the only ideal of a group is the group itself, because from any element of the group we can go to any other element of the group by left or by right multiplication. Example 3, if our semigroup S contains a 0, then this 0 is an ideal of S. That follows directly from the definition of the 0 element. And here is a more complicated example. Consider the full transformation semigroup Tn and let K be a positive integer which is less than or equal to n. Then we can consider inside Tn all elements which have rank at most k. And the collection of these elements is an ideal. This is due to the fact that the rank of the composition of alpha and beta is bounded from the above by ranks of alpha and beta. Now we can define the notion of a Riesz congruence. Let S be a semigroup and I an ideal of S. Consider the equivalence relation tilde on S, which has equivalence classes defined as follows. If A is not an element in I, then the equivalence class of A consists just of A. It's a singleton. And if A is in I, then the equivalence class of A is the whole of I. So we have singleton classes outside I, and the whole of I is one equivalence class. Proposition: this tilde is a congruence on S, and it's called the Riesz congruence corresponding to the ideal I. Proof: we have only one non-singleton equivalence class, namely I, so we need to check the congruence axioms for this equivalence class, only for it. Because everything else is a singleton, there the axioms are trivial. If A and B are elements in I and C is an element in S, then AC, BC, CA, and CB are elements in I because I is an ideal. And in particular, we get that AC is equivalent to BC and CA is equivalent to CB. And that's exactly what we needed to check. So this completes the proof of this proposition. So now, having this risk congruence, we can define the corresponding risk quotient. So let S be a semigroup and I an ideal of S. So we consider the corresponding risk congruence tilde on S, and then the definition, the quotient of S modulo this risk congruence tilde is called the risk quotient of S modulo I. For example, consider the additive semigroup of all positive integers. Then, for any m in this semigroup, we have the set Im, which consists of all elements which are greater than or equal to m. So it consists of m, m plus 1, m plus 2, and so on. And this is obviously an ideal of this semigroup. Let tilde sub m denote the corresponding risk congruence. Then we have the risk quotient of all positive integers by this congruence tilde sub m. And in this congruence, of course, the ideal Im becomes the zero element. So we have just seen an example which contained an infinite number of different congruences on the additive semigroup of all positive integers. Let's describe all congruences in this semigroup. We have just seen that for any m, a positive integer, we have the risk congruence tilde m, corresponding to the ideal Im, which consists of all elements which are greater than or equal to m. So are there any other congruences on this semigroup? The naive answer is yes, because we have the equality relation and it's definitely different from any of these tilde m's. Let's note that the full relation on our semigroup coincides with tilde 1. So the full relation is covered, but the equality relation is different. Any other congruences? So let's try to figure out what are the other congruences which we have on the semigroup of all positive integers with respect to addition. So assume that tilde is a congruence on this additive semigroup of all positive integers and that it is different from the equality relation. Then there should exist two different m and n such that they are congruent, such that m tilde n. So we can choose m and n such that m is smaller than n, the difference between n and m is minimal possible, and under this assumption m is minimal possible. Then, of course, m plus I is congruent to n plus I for all I. That's from the definition of the congruence. And this implies that m plus I is congruent to m plus k plus I, so k is a difference between n and m. And this is congruent to m plus 2k plus I, and this is congruent to and so on for all I. And so we have the classes which contains m, we denote it by a1, the class which contains m plus 1, we denote it by a2, and so on the class ak, which contains n minus 1. So these congruence classes are all different due to our minimality of k, so we choose k minimal possible. So we have these classes. So assume that some s which is smaller than m belongs to one of these ai's. Say s is equivalent to some m plus r. Then m minus 1 equals to s plus m minus s minus 1, and this is equivalent to m plus r plus m minus s minus 1 belongs to some aj. If j is strictly smaller than k, then we have that m minus 1 belongs to some aj with j strictly smaller than k, and because of the minimality of k, the difference between m minus 1 and the corresponding minimal element here is smaller than k. So this contradicts the minimality of k, so this is not possible. But if j is equal than k, then of course the difference between m plus 1 and n minus 1 is k. But then we have chosen m minimal possible, and this contradicts the minimality of m. As a consequence, we have that none of the elements which is strictly smaller than m belongs to any of our classes ai. Now let us assume that we have two elements S and T which are smaller than M, which are equivalent and which are different. So S is strictly smaller than T. Then we can add to both S and T, we add M minus T, and we get that M is equivalent to S plus M minus T, and this should belong to A1, and we get a contradiction with the minimality of M. So this means that all elements smaller than M form a singleton congruence class. So the congruence classes of our congruence are 1, 2, and so on, M minus 1, and then A1, A2, and so on, AK. And now we claim that for all M and for all K, the equivalence relation for the above classes is a congruence. And of course, we only need to check the axioms for the non-singleton classes. For singleton classes, there is nothing to check. And since each element in our semigroup is a sum of copies of 1, it is enough to check that if we have two elements A and B in some AI, then A plus 1 and B plus 1 belong to some AJ. But this is clearly true, so if I is not equal to K, then J is just I plus 1. And if I is equal to K, then J is 1. So J is I plus 1 modulo K. And we can now formulate this as follows. So theorem, let tilde be a congruence on the additive semigroup of all positive integers, different from the equality relation. Then there exists positive integers M and K, such that the tilde equivalence classes of this congruence, and we denote it by tilde M, K, are 1, 2, and so on, M minus 1, and then the class M, M plus K, M plus 2K, and so on, and then M plus 1, M plus 1 plus K, and so on, up to M plus K minus 1, M plus 2K minus 1, and so on. And in order to get the Riesz congruences, so Riesz congruences correspond here to the case where K is equal to 1. So this completes the description of all congruences on the additive semigroup of all positive integers. Finally, let us talk a little bit about monogenic semigroups. Definition: a semigroup S is called monogenic, provided that there is A in S, such that for any element B in S, there is a positive integer M with the property that B can be written as a product A times A times A times A, and so on, where we have M factors. So the notation is that the product A times A times A and so on with M factors is usually denoted by A to the power M. So if such element A exists, it is usually called the generator of S. Remark: a quotient of a monogenic semigroup is monogenic, quotient by any congruence. And of course we just take the class of the generator and it generates the quotient. So for example, the semigroup of all positive integers with respect to addition is monogenic, where the generator is the element 1. So any positive integer is a sum of copies of 1. Example 2, every cyclic group is a monogenic semigroup. So as a generator, we can choose any generator of this group as a group. Now we can formulate the following theorem, which classifies all monogenic semigroups. So let S be a monogenic semigroup. If S is infinite, then S is isomorphic to the additive semigroup of all positive integers. If S is finite, then S is isomorphic to the quotient of the additive semigroup of all positive integers by a congruence tilde mk for uniquely defined m and k. Proof: let A be a generator of S. If we map a positive integer I to the i's power of A, this of course defines a homomorphism from the additive semigroup of all positive integers to S, because a to the power I times a to the power j is equal to a to the power I plus j. So we have this homomorphism. It is surjective since S is monogenic, and so by the first isomorphism theorem, S is isomorphic to the quotient of the original semigroup, the additive semigroup of all positive integers, modulo the kernel of this homomorphism. The kernel must be a congruence on the additive semigroup of all positive integers, and we have just classified all congruences. So if the kernel is the equality relation, then S is infinite and is isomorphic to the semigroup of all positive integers. If the kernel is not the equality relation, it must be one of the tilde m sub k's, but then we have only finitely many equivalence classes, so in this case S is finite. And so we only need to argue that m and k are uniquely defined. So let's note that the quotient of the additive semigroup of all positive integers by tilde m comma k has m plus k minus 1 elements. So m plus k minus 1 is uniquely defined as the number of elements in the quotient. And to prove that either m or k is uniquely defined, which would then imply that both should be uniquely defined, it is easier to show that k is uniquely defined. And for this, one simply shows that the classes A1, A2, and so on, AK, form a cyclic group with k elements. So our monogenic semigroup contains a cyclic subgroup with k elements. And this implies that k is uniquely defined, and so both m and k are uniquely defined. Some additional problems and questions at the end. Problem question 1. Formulate and prove first isomorphism theorem for monoids. Problem question 2. Let I be an ideal of a semigroup S and tilde the corresponding Riesz congruence. Prove that I is the zero element of S modulo tilde. Problem question 3. Prove with all details that the quotient of a monogenic semigroup is monogenic. Problem question 4. Prove with all details that the classes A1, A2, and so on, AK form a cyclic group with k elements in the quotient of the additive semigroup of all positive integers by tilde m comma k. And problem question 5. Classify all congruences on T sub 2 and T sub 3. Thank you very much and see you next time.